Greetings! Today we're going to learn about greatest common divisor, GCD, and also proofs involving GCD. The greatest common divisor of integers a and b, we'll denote it as GCD a comma b. We'll often just hear people saying GCD instead of greatest common divisor. But the GCD is the largest integer, so the greatest common divisor. So the largest integer that divides both a and b, so it's a common divisor. So for example, if we are given 12 and 20, then we can do some scratch work over here. 12 is equal to 2 times 2 times 3, and 20 is equal to 2 times 2 times 5. So the greatest common divisor would be 4. 4 is the divisor of 12. 4 is also a divisor of 20. The 3 and the 5, they are primes that don't go into the other factors. Another example, suppose we have two primes, p and q. Then what is their greatest common divisor? Well, if p and q are the same, then it would actually be that number. So that would be p if p is equal to q. Now, if we have the same primes like 23, comma 23, then the greatest common divisor would be 23. But otherwise, it would be 1. The primes only have themselves and 1 as divisor, and so if they're different, then they wouldn't share divisors. How about 0 and 23? Now 23 has divisors 1 and 23. 23 would be the larger of the two, so that would be the answer, because every integer divides 0. 23 times 0 would be 0, so 23 divides 0. Now these edge cases are perhaps worth thinking about for a moment. GCD 0, 0. What's the largest number that divides both 0 and 0? Well, every integer divides 0, so there's not a biggest one. You can say 242, but then I can come up with an even bigger number that divides 0. And so this is undefined, and we'll avoid having both a and b be 0 from now on when we talk about GCD. Let's have a proof about something about GCD so we can play with it. Given what we just said, let's let a and b be integers, and then a and b are not both 0, and b not both 0. It will work as long as one of them is not 0, not both 0. Okay, so that's going to be our basic assumption all the time when we work with GCD. Then the GCD of a and b is equal to the GCD of a minus b and b. If you bring back the definition of GCD, it says that it's the greatest common divisor. So when you're trying to prove that two GCDs are equal, a very common technique is to prove that one is less than or equal to the other, and vice versa, so therefore they're equal. So let me show you how we could go about doing that. You can also pause for a moment and try to figure this out yourself for a bit, and then resume the video whenever you get stuck or when you have a good idea and want to see if I do it the same way or not. So as usual, we'll state some upfront assumptions. So I'm simply copying the same assumption from above, and then I would then start by going one way. So let's say let D equals the GCD of A comma B. So my goal is to show that D is less than or equal to the GCD of A minus B comma B. Right? So I want to somehow show that D is some divisor of A minus B and B. And as long as it's some divisor, then it's less than or equal to the greatest common divisor. So that's our strategy. So if we have D as a GCD of A comma B, then in particular D is a divisor of A, and D is a divisor of B. I'm not even going to talk about the fact that D is the greatest among them, right? Just the fact that D is a divisor of A. So then D divides A and D divides B. So D is a divisor of A, and D is a divisor of B. So we have that if D is a divisor of A, then A is equal to D times something, let me call it X, and B is equal to D times something, let me call it Y, for some integers. As usual, it's very important that these are integers, so we're always going to not be sloppy and really remember to write that. Now, then A minus B, that's this term right here. This is why I'm calculating it. Right? So then A minus B is equal to, we can just sub it in at dx minus dy. And then we can factor it out. Now once we have that, it follows that D is also a divisor of A minus B. So D divides A minus B. Now notice that D divides A minus B, and D of course still divides B, nothing has changed. So D is a common divisor of A minus B and B. Thus, D is a common divisor of A minus B and B. If it is a common divisor of A minus B and B, then it must be less than or equal to the greatest of the common divisors. So D is at most, well, I suppose I should say what D is right now because I'm about to be done. Right? So let me remind you that D was defined to be this left-hand side, right? But we just figured out that that's a common divisor of A minus B and B, so it's at most the greatest common divisor of A minus B and B. So that gives us one direction of the proof that shows that the left-hand side is at most the right-hand side. And now we need to reverse it, and the proof will be similar but not quite the same, and therefore we have to write it out. So I think right now it's polite to like maybe skip a line and then draw attention to the fact that we're going to do something different now. So I'll say now and let me not use D again. Perhaps use the next letter in the alphabet, E, and we'll set that to the equal the other side, the right-hand side. I would encourage you to pause the video right now and try to write out the second half. It's very similar. You just have to change a few things here and there. So E divides A minus B, and also B. And this is by definition. And so what that means is that, so we have A minus B is equal to, do you think I can keep using X and Y again? Let me reuse X and Y. So I suppose I could have reused D as well. So A minus B is D times, well, I suppose I didn't actually reuse D. I better write E. E times X, and B is equal to E times Y for some X, Y, and Z. So I'm not saying it's the same X, Y, but it's just the fact that it's true for some X, Y, so I'm reusing the X and Y. Maybe this is good. All right. So then, this time we are trying to calculate the left-hand side here. So A, we don't know what A is yet. So then A is equal to, well, that's equal to A minus B plus B. And A minus B is EX. And B is EY. And you know how it goes by this point, right? We can factor out the E. And then we see that we have divisibility going on. So so E divides A. So what we figured out is that E is a common divisor of A, we just figured that out, and also of B that it started with, of A and B. And if it's a common divisor, then it's at most the greatest common divisor. So GCD A minus B comma B is E. This is our definition right here. I'm about to be done, so I'm reminding you of that. And that's less than or equal to the greatest common divisor. So since it's a common divisor of A and B, it's bounded above by the common one. The greatest one. And perhaps we could write one more line here, but notice that, so here, GCD A comma B, I'll write this. Combining, we get GCD A comma B is less than or equal to GCD from above here. GCD A comma B is less than or equal to GCD A minus B comma B, and that's less than or equal to GCD A comma B. So if some number is less than or equal to some other number is less than or equal to the original number, that shows that they're actually all equal to begin with. So GCD A comma B is in fact equal to GCD A minus B comma B. And that's what we wanted to prove. So this proof is pretty involved. I want to say one more time, the general strategy when proving things about GCDs is to often try to show inequalities, because you want to leverage the fact that you have a greatest common divisor. So if you find a common divisor, then you'll get an inequality. In order to get equality, you will need to prove the inequality both ways. And one is less than the other, and the other way around, and then you'll get that they are equal. And we just proved that if we're trying to calculate GCD, we can subtract B from A and then calculate GCD of A minus B and B, and we'll get the same result. So what does this theorem get us? Well, we were focused on learning how to prove statements about GCD in this video, so I will end it here. But in a follow-up bonus video, we can see using this fact to calculate GCD more efficiently. All right, see you later. Bye.